In 1977, NASA launched two spacecraft with a clear job: fly past the outer planets, send back the first close-up look at alien worlds, and then, if they survived, keep going. The probes were called Voyager 1 and Voyager 2, and they did exactly what they were built to do. They transformed Jupiter into a living system of storms and lightning. They turned Saturn's rings from a blurry band into a world of structure. They revealed active moons, strange magnetic fields, and atmospheres that didn't behave like anything near Earth. But the most unsettling part of the Voyager story isn't what happened near the planets. It's what happened after the main mission ended, when both spacecraft kept drifting outward into a region where the familiar solar system stops feeling like a place and starts feeling like an influence. Because even far beyond Neptune, the Sun is still doing something. It's still blowing. The Sun constantly releases a stream of charged particles, mostly protons and electrons, called the solar wind. It's not just a breeze, it carries energy. It carries the Sun's magnetic field with it, and it shapes a vast bubble in space, the heliosphere. If the planets are the Sun's neighborhood, the heliosphere is the Sun's weather system, an enormous magnetic atmosphere that extends far past the last planet, wrapping the solar system in a moving, charged shell. For a long time, this bubble was a model on paper and a set of indirect clues. Scientists could estimate its shape from the way cosmic rays change near Earth, or from the way the solar wind behaves as it travels outward, or from faint ultraviolet signatures at great distances. But nobody had ever gone out there and touched the boundary directly, not until Voyager. As the probes traveled farther from the Sun, they watched the solar wind weaken and change. Closer in, the solar wind streams outward at hundreds of kilometers per second, but it doesn't expand forever in a clean, steady flow. Eventually, it runs into pressure from outside, the interstellar medium, the thin mixture of gas, dust, and plasma that fills the space between stars. Our solar system isn't sitting still, it's moving through the galaxy. That means the heliosphere is pushing outward, while the interstellar medium pushes back. The result isn't a simple edge like a brick wall. It's more like a set of boundary layers, the way weather changes when two air masses collide on Earth. Except out here, the air is plasma and magnetic fields, and the distances are beyond anything we intuitively grasp. At some point, the solar wind slows abruptly after plowing into that resistance. That slowdown is called the termination shock. Beyond it lies a chaotic region called the heliosheath, where the solar wind is no longer a fast, smooth outflow, but a compressed, turbulent, heated plasma that's being squeezed and redirected. And beyond the heliosheath is the boundary that matters most, the heliopause, the point where the outward pressure of the Sun's wind finally yields to the pressure of interstellar space. Scientists expected a boundary. They expected a transition. But what made the Voyager crossings feel like a storybook moment is how sharp some of the changes were, and how dramatic the environment sounds when you translate the physics into human words. This is where the viral phrase comes in: a 50,000-degree wall at the edge of the solar system. If you hear that and imagine a spacecraft slamming into a literal curtain of flame, you're picturing the wrong thing. Space out there is still unbelievably empty. You can have particles with tremendous energy, particles that, in a laboratory, you might describe with temperatures of tens of thousands of Kelvin or more, and still have almost no heat in the everyday sense, because there's hardly anything there to transfer that energy into your spacecraft. Temperature, in plasma physics, often describes the average energy of particles, not a roaring furnace you could warm your hands near. The wall isn't a solid structure. It's a region where particles are compressed, energized, and stirred up as two immense environments press into each other: the Sun's expanding plasma and the galaxy's background plasma. And the reason this boundary grabbed people's imagination is that Voyager didn't just confirm the heliopause exists. It turned the solar system's outer edge from an idea into measurements. Voyager 1 reached that frontier first. In 2012, its data showed it had entered a new regime. The radiation environment shifted, the population of high-energy particles changed, and the spacecraft began to register signals consistent with a denser plasma beyond the heliopause. Voyager 2 followed in 2018, crossing at a slightly different distance and carrying a different set of working instruments, which helped confirm the picture from another angle. Two separate machines, years apart, reaching the same kind of transition: humanity's first direct step from the Sun's domain into interstellar space. At the crossing, one of the biggest headline-worthy ideas is heating and compression. In the heliosheath near the boundary, the solar wind is slowed, squeezed, and churned. When flows of plasma collide and pile up, particle energies rise. That energized region has been described in popular language as a wall of fire, not because it's fire, but because it's a boundary where the physics becomes intense compared to the calmer, more predictable conditions closer to the Sun. Numbers like 30,000 to 50,000 Kelvin get used to communicate that intensity in human terms. A searing-sounding temperature that makes you feel, instantly, that this is not empty nothingness. It's a place where motion, pressure, and magnetic fields are doing real work. But the beautiful twist is this: despite how extreme those numbers sound, Voyager wasn't in danger. Not because it was armored against heat like a re-entry capsule, but because there's almost nothing to conduct heat into it. The frontier is violent in a plasma sense, not in a touch-it-and-burn sense. It's a storm in a near vacuum. The spacecraft glided through, and the real drama was in the instruments: the sudden changes in particle populations, the shift in magnetic conditions, the way the solar wind's fingerprints faded and the galaxy's fingerprints took over. Then Voyager delivered surprises that went beyond the headline. One surprise was that the two probes didn't cross at exactly the same distance. Voyager 1 crossed at roughly 121 astronomical units from the Sun. Voyager 2 crossed at roughly 119. An astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. So we're talking about a boundary more than 100 times farther out than Earth's orbit. That 2-unit difference might sound tiny on a cosmic scale, but it matters because it tells you the heliosphere isn't a rigid bubble. It's dynamic. It swells and shrinks with the Sun's activity, and it responds to changing conditions in the surrounding interstellar medium. The edge moves. It breathes. Another surprise involved magnetic fields. Before Voyager, many people expected a more obvious switch in magnetic field direction across the heliopause, like crossing a border where the internal field and the external field point in noticeably different directions. But the Voyagers found that the magnetic field inside and the magnetic field just outside weren't separated by the dramatic flip some models suggested. The fields appeared more similar in direction than expected, implying the transition could be smoother and more complex. A zone where fields can drape, mingle, and reconnect rather than forming a clean, simple divide. And that matters because magnetic fields aren't decoration out there. They're architecture. They guide charged particles. They determine how energy moves. They influence how cosmic radiation enters, or fails to enter, the heliosphere. Which brings us to what might be the most important reason this boundary matters. It's part of a shield. Outside the heliosphere, the galaxy is full of high-energy particles called galactic cosmic rays. They're born in violent places, supernova remnants, energetic stellar environments, distant events that accelerate particles to enormous speeds. When those particles reach the solar system, they don't just create pretty auroras. They can damage electronics, threaten astronaut health, and alter chemistry in atmospheres and surfaces over long timescales. The heliosphere helps reduce how many of these particles penetrate inward. It's not a perfect barrier, but it's a filter, more like a dynamic, magnetic sieve than a solid wall. Voyager's journey helped show that this shielding is not constant. It changes as the sun changes. When solar activity rises and the solar wind and magnetic conditions strengthen, the heliosphere can be more effective at deflecting cosmic rays. When the sun is quieter, the balance shifts. That has practical consequences for planning long-duration human missions beyond Earth's protective magnetosphere. The farther humans travel, the less Earth helps. Understanding the heliosphere's behavior becomes part of understanding the radiation environment future crews will face. And the implications don't stop with us. Every star with a wind creates its own version of this bubble, an astrosphere. If our heliosphere influences radiation conditions throughout the solar system, then other stars' astrospheres influence radiation conditions around their planets. That makes Voyager's measurements more than a one-off curiosity. They serve as a template, a real example of what a star's outer influence looks like when it collides with interstellar space. If you're trying to judge whether an exoplanet might maintain an atmosphere, or whether its surface is bombarded by harsh radiation, the nature of its star's bubble matters. Voyager turned the Sun's version from theory into something you can calibrate against. Meanwhile, the Voyagers themselves continue onward. Their power source weakens a little more each year, and NASA engineers carefully shut down instruments to conserve energy and keep communication alive as long as possible. The signals that reach Earth are faint, whispers from a distance so great that light itself takes many hours to cross it. Yet those whispers still carry real measurements: particle counts, magnetic field readings, plasma properties, and the changing background of interstellar space. They're sampling a region no other spacecraft has ever sampled, and they're doing it with technology designed in the 1970s. Eventually, in the coming years, their power will drop too far. The instruments will go quiet, the transmitters will fall silent, and the spacecraft will continue without us, drifting through interstellar space for unimaginable spans of time. That's the other reason people can't let go of this story. It's both scientific and strangely human. Voyager carries the golden record: sounds, images, and messages meant as a time capsule from Earth. It's not likely to be found, and it wasn't sent as a practical communication plan. It was sent as a gesture, a reminder that these machines are, in a very literal sense, pieces of our world traveling beyond the sun's reach. And Voyager's discoveries are now shaping what comes next. NASA and scientists have explored ideas for a dedicated interstellar probe, something faster, with modern instruments designed specifically to map the heliosphere in 3 dimensions, to watch the boundary change over time, and to measure the interstellar medium with the kind of detail Voyager could only hint at. A mission like that could answer a deeper question hiding behind the viral headline, "Is this turbulent, energized boundary a special feature of our sun's interaction with its local interstellar neighborhood? Or is it a common feature around stars throughout the Milky Way?" So if you strip away the metaphor and keep the reality, the 50,000-degree wall isn't a wall, and it isn't fire. It's something more interesting, a frontier where 2 giant environments meet and negotiate, where the sun's influence doesn't end with a neat line, but with a shifting, compressed, magnetized boundary that responds to pressure, motion, and time. Voyager went out expecting planets. It found an edge. And at that edge, it found proof that the solar system doesn't fade into emptiness. It transitions into a living interface between our star and the galaxy, a place where space itself has structure, weather, and force. Even after nearly half a century, those two spacecraft are still extending humanity's reach, not by imagination, not by telescope, but by presence. And the message from the frontier is simple. The outer solar system is not the end of the story. It's where the story opens into the sea between stars.